Hey everyone, Happy New Year and welcome to Community Conversations. My name is Liz Yang from the Growth Team. So Community Conversations is an opportunity for you, the community, to hear from contributors within the internet computer ecosystem, as well as ask them questions live. So the current design and implementation of the IC protocol has been focused on simplicity and low engineering effort. While this suffices to demonstrate the possibilities of Canister's smart contracts, unleashing the full capacity of the internet computer requires a high-performance design and implementation. Today, we will have senior researcher Stefan Kessler here to talk about the performance of the IC. Feel free to take it away, Stefan.
Thanks, Liz. Hi, everybody. Welcome. Thanks for joining in. Today, I'm going to talk about the performance of the internet computer. And this is really a team-wide effort, so I'm doing this on behalf of the entire team. To motivate this talk a little bit, I wanted to start off with this observation that if the IC was truly to become the blockchain singularity, it would be crucial that the performance and the cost of execution is similar to those of centralized cloud provider platforms. So what exactly is it that we have been doing in these last few months? We have been spending some time to evaluate the performance of the internet computer as it is now. We have been trying to ensure that we can run even relatively complex smart contracts on it. And we also want to make sure that we don't regress when we upgrade the IC further. This is important for various reasons. First of all, we need to know what the maximum capacity of the internet computer is, because we need to be able to plan ahead in adding more resources to it. We need to be prepared for future workloads, especially if we have these launches of new applications that can cause sort of spikes in the resource consumption, because a lot of people simultaneously try out something new. And perhaps most importantly, we also need this work to identify performance bottlenecks that we can then base our optimizations on. Before we get too much into the details, I would want to spend just one slide talking a little bit about what we don't do here. First of all, this is very early work. There is a lot that we still have to do. And so far, we have mostly been focusing on keeping the protocol as simple as possible and caring about correctness rather than performance. And obviously, this is going to change now. And I'm not going to talk about other blockchains here a lot, so there won't be comparisons of any sort. Right, so before we dive into the details, I wanted to talk a little bit about scalability and sort of the two types of scalability you can have in a system. So first, you can scale up a system. That means we want to improve the performance of a single node so that a single node in the system can process more requests per second without us having to add more resources. And that's obviously great because we don't need to add resources. But there are limits to it, because eventually we are going to run out of compute capacity on our machines because we reach the hardware limits. And often also we have things like synchronization issues because we have so much going on the same machine and we need to synchronize between various concurrent operations. And there is an overhead involved with that. So this is why we can also scale out. And that works by adding more resources into the system. And the way we can do this with the internet computer is we can add new subnetworks. That's really nice because the IC is already partitioned into subnetworks, and these subnetworks, they are relatively independent. So adding more is a relatively simple operation for us. The problem with that is that there might be less locality in the system. So if you imagine you have a big application that needs to communicate a lot, you might have to communicate more across subnetworks. So there are limits on how well this can work as well. And there might also be more pressure on the NNS. So currently, we don't think we are anywhere close to a problem here. But eventually, the NNS is sort of like a central component of our system might become a bottleneck. We could also think of adding more nodes to an individual subnetwork. And that is great for the query performance. So queries are read-only calls into the internet computer, and they're sort of local operations on a single machine. If you do a query call against a machine, that machine can handle that query all by itself. It doesn't need to talk to anybody. So adding more machines to a subnetwork immediately gives us better query performance. because we have more machines to talk to. But it might hurt update performance, because now if we want to do an update call, which changes the state of the system, we need to make sure we execute all these updates in the same order. So we need to run consensus on it. And consensus tends to get more expensive the more nodes have to talk to each other. So we think we need both scale out and scale up. Right, so what we have been doing recently is we have been developing this benchmarking suite that I would like to talk about today. And before we do that, I would like to first briefly show again how the internet computer is structured. So what we see here is a single subnetwork of the internet computer. And we have a bunch of replicas here, and they all talk to each other. Currently, this is all-to-all communication, sort of. And we also have those boundary nodes that users are talking to. And again, there are these two types of calls. It's a little bit simplified. There are more than that, but the ones that we care for in this talk are the query calls and the update calls. And a user would send those against the boundary nodes, and the boundary nodes would then sort of make sure that they are properly load balanced across all IC replicas, typically in a round robin manner. So they would always go around sending messages.
Stefan, quick question from the chat. So one of the community members is asking, just looking at the slide, couldn't read throughput just be increased by adding read replicas that don't participate in consensus, hence not increasing update latency, but adding read throughput?
Yeah, that is something we have been thinking about before, and that likely would work, yes.
Awesome. Thanks, Stefan, and thanks for Slycott for asking the question.
Right. So the boundary nodes do a load balancing, but they also sort of, we use them as a rate limiter also to protect the IC from DDoS attacks or anything like that. So these two reasons are reasons that when we measure the scalability of the IC and anything related to performance, we are not really using the boundary nodes, because we need fine-grained control over which replicas we talk to, and we also don't want to measure the rate limiter in the boundary nodes, right? If you would run against the boundary node, we would just get the number that is hard-coded in there. So what we do instead is we have this benchmarking suite that essentially is a process manager, if you will, and it's meant to provide like a sane experimental setup that ensures that whenever you run an experiment, you really measure what you want to measure, and you're not running into unforeseen bottlenecks anywhere. An example for that is having enough machines that generate load. So the first thing that Benchmark Suite is going to do, it's going to spin up a bunch of load generators that generate the load that we want to evaluate. And then depending on the types of workloads we want to look at, it chooses which nodes to address the workload against. So for query calls, typically we want to send all of the queries to a single IC replica. As I said before, these are local operations. So if we would send them to multiple IC replicas, we wouldn't really win anything, because they are anyways executed independently. We would just need many more load generators. But for update calls, we need to address all IC replicas. And the reason for that is that in order to, as I said before, in order to, before we can execute those updates, we need to order them, and the order is done by consensus. And in order for consensus to happen, a majority of the machines need to see those update calls beforehand. So we need to send them around to everybody first. Now, if we target always one single replica with the update calls, that single replica would have to broadcast those update calls to everybody else, and we will create a bottleneck in the network. So it's very important that if we want to stress a subnetwork with update calls, we send those equally to all replicas in the subnetwork. Right, and then what the benchmark suite is going to do, essentially, very simplified, it's going to try to record as much data as possible and persist it. And the recording is supposed to happen in a way that it's self-contained. So if you just see the recorded data later on, and you want to reason about the performance, and you want to figure out what happened in the system, you can entirely, by looking at that data, reconstruct what happened. So amongst other things, we collect system metrics such as the CPU utilization or the IPC of the CPUs. We also have some memory-related metrics. We want to have a look at the throughput that we achieve when fetching data from memory. And also we want to look at stalls, so how often a CPU has to wait for memory to arrive. We also collect metrics from the replica as well as from the clients. I will talk a little bit more about that later. Now, after we have recorded all that data and the benchmark has terminated, we have a bunch of tools that can look at that data and generate reports out of it. And the separation between a recording phase and an analysis phase is sort of really nice because you can have multiple tools that look at the data. So for example, we have one tool that generates a report for a single execution of a benchmark, but we also have a tool that can look at multiple of those benchmarks and compare them or generate a dashboard out of it or something like that. Then when we launch a benchmark, essentially almost always we want to run iterations where in each iteration of the benchmark we increase the load. So in this example here, the numbers that don't really matter here, it's more about the shape of that. On the x-axis we see the time, and on the y-axis we see the load. We have this red horizontal line in the middle, which is sort of the target workload that we are addressing, target load. And then we see those boxes of load where each box is sort of one iteration of the benchmark. And you can see that over time, we increase the load. And we do so in a way that we have more measurement points around the value that we think is the maximum capacity, because that's where we really care for the details. If you think about it, right, when we run a very low sort of load, we don't really expect to see any errors, or we don't expect the latency to be unusually high. But once we reach a point at which the system sort of starts to struggle, then we begin to see failures and maybe spikes in latency. And this is why we want more data points here, because we want a lot of detail about what happens around that point of time. Another way of plotting this is by having the iterations on the x-axis and the load on the y-axis. And you can see here with this orange sort of target load that we are looking at, we have a lot of measurements around there. And then the further we move away from that, the further also it jumps up with each iteration. So we are able to really stress the system. So in that example here, if the target load is something like 2,500 requests per second, we can stress up to 25,000 requests per second, which is 10x more than what we would expect the system to handle. I will talk a little bit more about this later, why this is important. We also have a tool that is called the workload generator, which we have been developing a while ago. And essentially what it does is it generates a large number of requests that is configurable for a certain amount of time. And it does so in a very even or uniform manner. So it's supposed to keep that desired request per second request rate as stably as possible. And we support a bunch of workloads here, so that can also be configured. And what the tool then does is for each of the requests it executes, it will collect the return code and remember the latency. And you can also then do statistics on it, and it will tell you what the median latency is and all of that. In addition, it will also export metrics that they give much more detail and also live information about what happens in the system that as a developer you can look at to see what the system does. The tool is written in Rust, and it's part of our code base. If you want to have a look at it, it was quite interesting to write it. We used a lot of async Rust there to allow a large number of outstanding requests. Right. Another way of understanding what the workload generator does is to sort of look at another experiment run, just as an example, where we again have the experiment time on the x-axis, and we have the the request rate that a set of 5 workload generators generate on the y-axis, and these are stacked plots. So each of these boxes, again, is one iteration of the benchmark, and each color here is a workload generator, and those are all running concurrently. And I think what is most interesting to look at is that those boxes, the top is almost flat, which means that the request rate that the workload generator can generate is extremely stable, and that's very important to us. It's not so true anymore. When we really stress the system, then we can also see that it starts to get a bit jittery, but it's a relatively nice tool to use. Next, I would like to talk a little bit about flame graphs, which is one of the metrics we collect during experimental execution, and it's not something we have invented or anything like that. It's a relatively standard tool, but it's sort of nice, so I wanted to mention it here. So in order to do flame graphs, what we have to do is periodically sample the stack traces of the program. So every, I don't know how many milliseconds, we look at where what sort of the code we currently execute, and we remember that. And later we look at that data and we group everything by function, and we get something like this out of it. So that's one example for the flame graph, and let me quickly try to explain how to look at the data. So first of all, the color doesn't really mean anything. The color is just a shade of red, if you wish, so that it looks like a flame. And the x-axis also doesn't really have a meaning other than the size of those boxes you see in the x direction. Let me just open a live example, see if that works. Sorry. So what this is here is an SVG image that is typically the output of a flame graph, and that's sort of nice because it's an image that if you open it in a browser, it's sort of interactive. So you can now hover over those boxes here to see how much time is spent in each of those boxes. So if I was an engineer that would care about, say, query execution, I could see that during the time when this benchmark has been recorded, 5.5% of time was spent in query execution. And then I can click on it, and then it sort of zooms in, and then I see what has been called from query execution in these 5% of the samples. And for example, I see that there's a few text wait in here, so there's a log somewhere here as well. Here we have been waiting, waiting in a receiver for a message to be received on a channel. So we get a lot of details about where time is spent, and we can, as somebody writing the code, it's a very nice tool to see if the intuition that we have about where time should be spent is actually true.
Hey, Stefan, a quick question from the chat. So from your earlier slides with the earlier graphs, does that show queries or updates?
I could check, but it doesn't really matter. So I was getting more at the shape rather than, in a second, this one?
I think Jordan was saying just in general, yeah.
I think probably this one is updates per second in one of the subnetworks we have internally one of the test nets we have internally. So none of these numbers that you have seen so far are in Mainnet or anything like that.
Okay, got it. Yeah. So Jordan was saying in the chat that the graphs don't say what kind of request, so it's hard to interpret since there's a big difference between a query and an update. And Ted was also saying it might be interesting to see a third axis and show the impact of scaling either out or up.
Yeah, so we will have some real numbers later. This is more to show what the tool does.
Okay, awesome.
And
Thank you.
We will look at numbers from Mainnet, and we will also look at some of the numbers we have internally as well since November when we released numbers.
Okay, thank you so much, Stefan. Also very big fan of the flame graph.
Okay, so let's see if I can get this back to full screen. Sorry for that. Right, so those are the flame graphs, and this is something that we typically use a lot to figure out where performance goes. Another thing we do is, and I think that's quite industry standard, is we use a lot of metrics that all the replicas expose. And the way this works is that each replica has a separate HTTP endpoint that serves those metrics. And then we use a tool called Prometheus that periodically pulls from those endpoints and persists the data it gets there. And finally, there is Grafana, which is a tool that generates dashboards out of the data stored in Prometheus. And that gives us a pretty good understanding of what the system does, because essentially each component that we have in the replica exposes some of those metrics that are well understood by the teams that are expert for those components, and they can go and look what's happening in the system. The benchmark suite can also simulate failures, or at least it's in the process of being able to do failures. That's important for us because obviously we want to make sure that the performance of the internet computer isn't only good in the case of like good network conditions. We also want it to be good when there are suboptimal network conditions, like maybe a link is slow, or maybe a link is currently down, or even if a machine is down. So these are the sort of things we would like to be able to do as well. And we want that to be sort of orthogonal. So we want to be able to run every benchmark we have with and without failure simulation. Then I would like to spend a little bit of time to talk about workloads. So maybe that will also help answer the second question a bit. So one workload that we have that is extremely useful, although it might not seem like it, is the counter canister. So that's a canister that stores a single value, and that value can be read with a query call, and it can be incremented with an update call. And the canister is extremely simple, which makes it almost like a no-op canister. It almost does nothing. So it's like a system baseline essentially, right? So this tells us how the system behaves independent of the canister, because we spend almost no time in the canisters. And it's all on a single page. It doesn't do orthogonal persistence. It doesn't do any messaging or anything like that. It's really extremely simple, and that makes it so meaningful, because if something goes wrong here, it's easier for us to figure out where to start looking for the problem. We have a bunch of more workloads. We have a memory test canister where we can read and write a lot of memory, and the size of the memory that should be touched can be configured with an argument in the message. So that's really, really nice. We have a crossnet test where you can specify the topology that you want to communicate. But it's like an overlay, essentially. You can configure an overlay that expresses how the communication pattern should be. So you typically deploy one canister in each subnetwork and then tell them how to talk to each other. And all of the benchmarks I've mentioned so far are sort of like micro benchmarks, right? They are targeted at stressing a single well-known resource, essentially. But we also are working on some macro benchmarks that are perhaps more realistic in the sense that they provide really useful functionality. One of the first ones we have been doing recently is a benchmark for the People Party project, where, if you don't know about it, so the People Party project is a way to sort of approve or make sure that internet identities are valid, by similar to what you would have done with PGP and these key signing methods for emails, where a bunch of people verify each other's validity. And the way the benchmark works is that there are certain phases. So first the party is created, then people can register for that party. When the party starts, they can join the party, and then there are phases where in each phase there is groups of people are formed, and then they sort of approve each other. So that's sort of like a real world benchmark. It was much harder to write, of course, because for that benchmark you need to follow the flow properly, right? You cannot just vote on each other without joining a party first. You need to make sure that every person that joins this party follows the correct flow. In general, one of the points where it would be really nice to also get some feedback on is for good ideas on what sort of workloads would be interesting to measure on top of what we already have. And we are very, very eager to learn what you think. Another thing we would like to do, and that follows up a bit on the previous point, is to add support for replaying real traces. Because for some of the even more complex canisters than what we have seen for the people party canister, it would be very hard to sort of emulate the same application logic in the benchmark. What you would rather want to do is you would just spin up a testnet or something like that, and you would just deploy the canister, and you would have like the web front end or whatever be used by a bunch of people, and you would just want to record all the update and query calls that have been issued by the users and replay them. That would be really nice. You could also play like with the speed up, like you could make them play faster or slower, or maybe you could drop some and see what happens. It's all really nice. It's just not that easy to do because we have time to live and expiry in some of the ingress messages, and the messages are signed, so just replaying them isn't directly possible, right, by design. So we would have to work around that. And the other issue is that in order for those messages to be replayed, we would have to make sure that the canister state is exactly the same, because it's possible that if you just record a trace of messages and you replay it and the state in the canister doesn't match, that these messages don't make any sense. So it's really nice to have such traces, but it's also not that easy to do. On top of sort of the canister and the logic in the canister, we can then choose the dimensions that we want to scale out. So for example, what some of the typical things we do is increase the number of requests per second for these canisters, or increase the payload size of the messages we send. We can also do things like growing a canister state until things start failing and see what sort of problems we see there. We have a benchmark that installs just a lot of canisters. We don't really do anything with the canisters, we just install them and see how the system behaves. But we can also do things like vary the size of, the number of nodes in a subnetwork, and see how, for example, gossip handles the increase in messages that need to be sent around between nodes. Right, and with that, I would like to show you some numbers we have collected. And I would like to start off with numbers from Mainnet, and those are the numbers that we already have presented around November. So some of you might already know them. Before we look at the numbers, there's just a few words I would want to say. So first of all, they're very conservative numbers, right? So this is Mainnet, so we didn't want to stress it too much because there are users on it, and we didn't want to have any user perceived impact with what we're doing. But we skipped the boundary node, so you couldn't directly reproduce what we show you here outside of the VPN. But that being said, changing the number that is currently hard-coded in the boundary nodes is a relatively simple operation, so it's very important for us to know what the system actually can handle. And the way the benchmarks works is relatively simple. We just essentially run one benchmark per subnetwork and aggregate all the numbers. And what that means is you need a lot of workload generators because the internet computer now with, I don't know exactly 30 subnetworks or something like that, and I don't know, 500 machines, it's a beast, right? And in order to stress it, you also need a lot of machines to generate the load against it. Okay, so let's have a look at it. So first of all, we have update calls. And what we have been doing is we have been sending update requests to almost all subnetworks. I think there are like 2 or 3 that we didn't send any messages to because they were already too busy. But we did so for around 5 minutes. So it's not that we just send a single spike and that would be queued somewhere or something like that. So this is really sustained throughput. And we managed to achieve something like 11,500 updates per second over a period of 5 minutes. And what I would also like to say here is that the way we count the number of updates that we have been executing per second is to look at how many messages per second the execution layer has been executing. So these are real numbers, right? This is the number of times we have modified the state in the canister. And likewise for queries. So here, because queries are a little bit, I would say, cheaper to execute, we actually did a bit more of an aggressive stressing here, and we have also increased the load over time. What you can see here is that in the end, we were able to achieve more than 250,000 queries per second over a period of, I don't know exactly that is, but for sure more than 5 minutes. So the entire benchmark, as you can see, is around an hour, right? And I think each block here is around 5 minutes. Right, and both of these, the number of queries per second and the number of updates per second, I've showed you here, they have been done with the counter canister. So we haven't really stressed the execution layer a lot. We have been focusing on the rest of the system. So obviously, if you would have a more complex workload, you would have lower numbers here. Right. A lot has happened since then. So I would like to also spend some time to show you a little bit what we have internally. So internally, we have a continuous delivery pipeline that periodically runs some performance tests on a dedicated testnet, which has a configuration that is roughly the same as what we would have on Mainnet. We are much more aggressively stressing in our testnet because we don't care as much if we break something. So we go typically up to 10x the request per second that we would normally expect to be able to handle. In addition to the weekly tests that we do automatically, you can also trigger it manually, which is sort of cool if you have a change that you're not sure how it will do. You can just run it and see what happens. And we also have dashboards to monitor performance trends over time. And from those dashboards, I would like to show you a few numbers. So the first is for the number of updates per second we can handle in a single testnet. And as you can see here, we have improved this a little bit since November. So we were able to do around 500 updates per second before per subnetwork. And now with around 8% improvement, we are up to around 550 or so updates per second per subnetwork. So what that really means is that with the current setup, so currently we have 29 application subnets, or at least when I started doing this presentation. So in theory, that should allow us to go at least up to 16,000 updates per second on the entire internet computer, which I think is pretty cool. We're very happy with that. In terms of queries per second, oh, sorry, one more thing. So even this number here is relatively conservative, right? So in those benchmarks here, we determine what the maximum capacity of a subnetwork is, but the way we define maximum capacity is still sort of conservative in the sense that it's the number of updates per second you can handle without a lot of failures. I think it's less than 20% failures or something like that. But if you continue firing beyond that point and you still count how many updates per second you can handle, you can actually go higher. And we have seen up to 600 updates per second in that subnetwork. We just don't really count it because there are failures happening here, at least some. And you can see that this is the last iteration we have been doing. So who knows what happens if we stress more. Now for queries, we had a very, very big improvement since we have been doing the last benchmarks. That's probably related to using more threads in execution that can concurrently execute queries. And while we have been seeing around 1,500 queries per second, we are now almost up to 3,000. So this is an 87% improvement. And with that, we think we can achieve a theoretical throughput of more than 1 million queries per second on the current mainnet configuration. So there is room for improvement here for sure. What's very important for us, I was hinting at it a little bit before, is that it's important to have a good high maximum capacity. But what's perhaps even more important is that if we push beyond that point, we sort of fail gracefully. We want to be in a situation that if we exceed the maximum capacity, first of all, the system doesn't break, but second of all, we can still handle the same number of requests successfully. So it's just that a lot of them get rejected, but the number of requests that can be handled per second shouldn't go down. And that's something you can see here, because what we do here in blue are the successful requests, which are increasing over time until a point when we start seeing failures. And then a certain number of them, a certain fraction of them get rejected, and that's the orange ones here. And then if we continue stressing even more, we just see a lot of more messages rejected because we know that we cannot handle them. But we still see roughly the same amount of messages being processed, which is something we think is very cool. And that brings me to the last slide, which is a collection of some of the ideas that we are having for possible performance improvements, because we think that this is just the beginning and we can achieve much better performance still in the future. One very sort of obvious low-hanging fruit perhaps is to have more concurrency in the execution layer. It's not super trivial to do that, obviously, because with concurrency you also have synchronization issues, and you need to make sure you don't end up into sort of lock contention issues. But there is some room for improvement here still. We do a lot of costly memory mappings because we don't know beforehand what sort of memory pages the canister will access, and we sort of dynamically need to map them into the canister address space when it's accessing it. And that's a relatively expensive operation, and we think, or we have showed, that we can amortize the cost of that a little bit by batching how we map pages. We spend a lot of time in crypto operations, which we might be able to improve further. That's certainly very interesting because we just have a sheer amount of them. So that's a good candidate, I think, for future improvements. And then I would like to remind you, perhaps in the end here, that so far the protocol has been designed for simplicity and correctness, and not so much for performance. So once we start thinking a little bit more about performance, there are likely going to be a bunch of things we can do here. And of course, there are many more things we can envision doing. We can use more hardware support. For example, we could offload things to crypto processors, or we could offload network operations to smart NICs or something like that. We could also make sure we need to enter the kernel less. Like every time you go into the kernel, it's a very expensive operation because you lose a lot of the application state in the process. And we have to do that currently for a lot of network-related operations, and also for the previously mentioned mapping operations. So there is a good chance we can improve that a little bit with the user-level network stack, or maybe more user-level scheduling. So there is room here as well. And with that, I would like to conclude, and I'm happy to take questions.
Awesome. Thank you, Stefan, for that very engaging talk. We have a ton of questions for you, so not to put you in the hot seat, but I hope you're ready. Cool. So Stefan, first question here. Are you looking into multi-threaded WASM? Once standardized and implemented in WASM environments, how do you expect that to improve query and update performance?
So to be honest, I'm not sure if we're looking into it. But I'm also not sure how useful it would be. So the problem with updates is that you cannot really execute update calls into the same canister concurrently, because you need to make sure that in order to do the same state transformations on each replica, you need to make sure you always execute all the updates in the same order on each machine. So you cannot really do concurrent updates on the same replica. For query calls, you could probably do it, but you could also just have multiple WASM runtimes. And in fact, we are working on having a more sandboxed approach where canisters are executing in their own processes. And it would be relatively easy, I think, to scale that up. You could, for example, imagine that you have multiple such canister processes for the same canister. So that should be possible, even without having a runtime that can do more concurrency.
Great, thank you, Stefan. So the next question, I think you covered, but just for the case, just to be thorough, are the benchmark findings available anywhere to read? Would be interested in checking it out. You covered that in your slides, so I think we can just include that.
Yeah, but I would want to maybe say a little bit more about it.
Okay.
So, the numbers I presented from November, they're all public. We already have, I think, probably the best place to look at it is the wiki we have. I think at wiki.dfinity.org or something like that. You will find it. We are also thinking of maybe, so we have, as I mentioned, we have these weekly benchmarks that we are running, and we create a performance dashboard out of it. And we are considering to have that public as well.
Okay, awesome. Thank you so much. So next question, are you planning on allowing Canister developers to run their own benchmarks, either locally or live? A big problem for me is measuring the cycle performance of the tools I'm building. It's difficult right now since gas cost can only be read on the live network and vary imprecisely.
That's a good question. I don't think I can answer that. I don't know. Sorry.
I know we have a lot of Dfinity people on the call, so
yeah, maybe somebody.
If somebody else can answer that in the chat, that would be great. Awesome. So next question, is there a set of small, medium, and large calls, both query and update? Whoa, this question is very long. Let me read this over. Okay. And are these, okay. Sorry, it's like 5 questions in one sentence as a run-on sentence. So I'm going to have to read that over. I'm going to skip to the next question. I cannot recall offhand. When a packet goes through the subnet discovery process, is there any form of routing, cache or whatever, in order to facilitate a faster traversal for subsequent packets?
Yeah, so I think what you're referring to probably is what the boundary nodes are currently doing. So the boundary nodes, when you send a request to the boundary node, it looks at what canister ID you're addressing, and it will look up with the routing table that comes from the NNS, which subnetwork is hosting that canister. And then it will send the request to the correct subnetwork. So there are parts of it that are cached for sure. So for sure, what the boundary node is doing, it's periodically, I guess, updating the routing table. It's certainly not doing this for every call, but I'm not sure if the mapping from canister ID to subnetwork is cached. Maybe also somebody else on the chat knows that.
Great, thank you, Stefan. So next question, what happens if more load is put than what can be processed? Do messages get queued?
They get queued for a little while, but the queue is not infinite, right? So the number of slots in the queue has an upper limit, and then we create back pressure, and then eventually the HTTP handler will reject messages, and we have a special return code for that, which indicates that the system is busy and it cannot handle more requests per second. That's what I wanted to show with this slide here. So once you reach a point where you start rejecting things, you can still continue processing the same amount of messages successfully. It's just that the rest immediately gets rejected so that they don't spend a lot of resources.
Great, thank you, Stefan. Next question, what is the update actually doing? Could we see what the request is?
So most of the numbers you have seen here is the counter canister. So what the update does is just increment the counter. So it doesn't have a payload, right? Because the function knows that it should increment the counter by 1. I can actually show you the code, but it's extremely simple. I think I put a link somewhere. Sorry for the. So this is the code of the counter canister. It's in WAT, so this is the sort of text representation of WASM, and it literally only has these two functions to read and write, and it's basically, you know, that's all it does. It just increments it by 1.
Okay, thank you, Stefan. Next question, was the 550 updates per second against a single counter canister or multiple on a subnet?
That's a good question. I think it's against multiple, but I don't think it makes a difference, actually. I think we tried both and it didn't make a difference for the counter canister because you spend relatively little time actually in execution. If you would have a canister where the work that you do for each update call is relatively long, then you would probably want to drive against multiple canisters, right? So that execution can execute those requests concurrently. But I don't think it mattered for the counter canister.
Okay, thank you, Stefan. Next question, is there any log where we could see if there was a failure?
I mean, you should see it from the request code, I believe. Unless I'm mistaken, right? Like if you run a request against the internet computer, you will get a response code that will tell you what happened. And there is a code, I think it's 429 or something like that, that indicates that the request got rejected because the system is too busy. You will probably not see that because it's actually something I didn't mention. We are currently far away from reaching capacity of the IC. So you're very unlikely to see your message being rejected because the IC is too busy.
Okay, awesome. So moving on to the next question, what were the cycles costs for those performance tests?
I don't know, but not that high. I think we put something like 10 ICP or something, but we didn't use all of it. So it was not that bad. I think the reason for that is so that we for query calls, there is not the high cost, right? It's a matter of installing the canisters and that's it. For the updates, I think the cost wasn't that high because we haven't been running it for very long. We knew essentially what the maximum capacity was, and we just did a 5 minutes run at that capacity. So it was okay.
Cool. Thank you. Next question. What are your thoughts on subnet load balancing and automatic subnet scaling? For example, splitting subnets that get too large, automatically adding read replicas as needed.
Yeah, we definitely need that in the future. I don't think we have been spending a lot of time on it right now, mostly because we didn't need it so far, because we are not reaching capacity anywhere really. But in the future, we definitely need that. Yeah.
Cool. Next question. How many canisters can be run on a single subnet?
So we are currently running experiments on that. And I think we can for sure install more than 100,000 canisters in a single subnetwork. We haven't spent a lot of time experimenting how responsive the subnetwork still is. The expectation would be that it's not like the responsiveness of the subnetwork is not impacted by the number of canisters that are installed, but we need to verify that this is actually true. But we did run a subnetwork with 100,000 canisters and it worked.
Okay. So just quick note, we are nearing the end of the questions. So if you want to keep this lively discussion going, please go ahead and add more questions to the chat or the Q&A box. And thank you, Stefan and team for being such a good sport about all of this. Cool. So next question, do you foresee increased performance leading to reduced cycle costs for running canisters?
I don't think I'm the right person to answer that question.
Okay. If someone from the Dfinity team in the chat can answer that question, that would be great. So we have a follow-up question from the previous question around like the 550 updates per second. Was that against a single counter canister or multiple on a subnet? So Hazel asked that question. She's saying, I would have expected the performance to increase by adding more canisters onto the subnet? Maybe I'm not clear on what the 550 updates per second represents.
So I think that depends where the bottleneck is. If the bottleneck when you run 550 requests per second is that you are queuing up things in execution, and execution cannot keep up with executing those updates in time, then it would help to have more canisters, right? Because you could have execution execute multiple updates for different canisters concurrently. We don't think that this is the case. I think what we have been measuring is the case when consensus, essentially, or the networking layer or whatever, is the bottleneck. And in that case, adding more canisters doesn't help, because the bottleneck is how quickly you can finalize blocks. And if the ingress messages in those blocks are for a single canister or for multiple different canisters, doesn't make a difference. So it depends what the bottleneck is.
Cool. And Yvonne also answered in the chat to Hazel. She said there is a limit on the number of messages per block, regardless of the number of canisters on the subnet.
Yeah.
Cool. So next question, how does the system decide what messages to drop?
I think there is no complex logic in there. It doesn't distinguish between, like, it doesn't look at the message in order to decide if it should be dropped or not. Like, there isn't a prioritization currently or anything like that. It's just when the system is full, it's going to drop a message, and it doesn't really care what the message is.
And so we've come to our last question for today. If people have additional questions and again want to continue the dialogue, feel free to continue asking. The question's from Paul. He's saying all of these tests are artificial. What can we expect from real world performance?
They are artificial in the sense that if you would write a canister yourself, it would obviously not behave the way our test canisters do. But our test canisters are designed in a way that they stress individual resources. And in the end of the day, when you write a canister, you will also be bottlenecked by a single resource. So if we identify resources that we're typically bottlenecked on, and we improve those bottlenecks, then that will help you too, even if your canister is more complex. That being said, we do want to run benchmarks with more complex workloads. And even with something as simple as the counter canister, there is still a lot we can do to make it behave a little bit more closer to reality. And one of the things we are looking into doing is we want to look at Mainnet, and we want to see on average how many pages, for example, a canister touches, how big in pages the canister code is. And we can just have something similar to the counter canister that exposes sort of similar behavior in all those important metrics without needing to have the same application workloads necessarily. Just, I hope that answers the question. So we think that we can have a simple canister, which, without doing any useful work, it will sort of stress the same resources as an average canister on Mainnet does. And we are going to look into that. That being said, if you look at the dashboards for Mainnet, there is a large number of requests that do very simple things. We can see that from our dashboard. So I don't think that what we have been doing so far is that far off from reality, to be honest.
Cool. Thank you, Stefan. We did get a couple of additional questions. So next question, currently, how do new subnets spin up? Are they started manually by the Dfinity team? And is there any more detail you can share around that?
I can talk a little bit about that, but it's not really related to performance, I would say. So if we add a new subnetwork, I believe there is an NNS proposal that says, should we make a new subnetwork, and then it gets approved, and then we have a new subnetwork.
Well, when you put it like that. All right. So final question, potentially, for now. This is the original question that my brain could not comprehend earlier in the chat, and Matthew has very graciously rephrased it. Okay. Can you do small, medium, and large tests instead of just the counter, i.e. a large data update, medium data update, so we can see behavior extremes?
Yeah, so we already have this memory test canister that touches a lot of memory pages, and we are running that internally with super big memory footprint, so to say. And we have some numbers on it, I just don't have it readily available here. And obviously the number of requests per second that you can execute if you copy around a lot of memory is drastically lower, obviously. But I don't know from the top of my head what this number is. I hope that we can publish the numbers that we have internally. I don't think there is anything secretive about it. It's just a matter of getting approval for having them.
Totally understand.
Externally. But what you can do, you can look at, so the benchmarking code is open source as well. It's part of the Divinity repository. So you can just look at the benchmarks and see what they're doing. And I've also linked for each of the benchmarks, I have a link here that goes to the public repo, and you can have a look at what those benchmarks do.
Okay, yeah, no, that's really fantastic. And for everyone tuning in, we're gonna make these slides public as well. So we want to here and the end of the questions. So unless anybody has any last questions, thank you so much to Stefan for such a thorough presentation. Stefan and team, shall I say. I know it's a team effort. Thank you for everyone in the community for your excellent questions, and thanks for all the Divinity team members who've been chiming in as well. So we look forward to seeing everyone at the next community conversation and see you all around. Bye everyone, take care.
Thanks for joining, bye-bye.